Welcome to this explainer. Okay, we're diving straight into a massive paradigm shift happening right now in software engineering. We're literally moving through a fundamental structural transition. For decades, right, a developer's core value was tied to typing out syntax, line by line. But that's changing, rapidly. We're moving away from manual instruction-level coding and stepping into what we call high-level intent orchestration. Instead of telling the computer exactly how to write every single loop or function, developers are becoming cognitive supervisors. We're guiding autonomous agents through complex architectural designs.
Picture a whiteboard split right down the middle. Over on the left side, you've got the old way of doing things, just frantic, manual typing of imperative shell commands. It's this chaotic, endless stream of terminal execution, debugging, and line-by-line syntax generation. Honestly, it's kind of overwhelming. Now contrast that with the right side. This is the new era. You've got the calm, clean design of declarative target states. It represents an engineer architecting boundary conditions, defining exactly what the system should achieve rather than how it should get there. The value has completely migrated from that frantic syntax typing on the left to defining intent and supervising agents on the right.
Section 1. Defining invariants, architectural boundaries. To actually pull off this calm, clean orchestration, we first have to understand how to set boundaries for these highly capable autonomous agents. Because, generative models, no matter how advanced they get, they can't just implicitly guess your business rules or your organization's security policies. You have to establish them. We call these architectural invariants. Persistent architectural rules, invariant patterns, and explicitly forbidden anti-patterns established across your entire code base. Think of these as rigid physical walls. These thick walls literally block an AI agent from breaking your public APIs, altering protected directories, or messing up your overarching system design. You're basically building a physical maze that the agent has to navigate safely.
So, what does this actually sound like in practice? Well, instead of giving step-by-step procedural instructions, like, open auth.py, add a function, call it here, you use a strong declarative constraint. You'd say something like, implement JWT validation, ensuring all tokens expire within 15 minutes, public endpoints remain unauthenticated, and existing integration tests pass without modifying test assertions. See the difference? That single sentence acts as a cognitive bounding box. It forces the agent into a safe, verifiable space where it knows exactly what success looks like and, crucially, what actions are strictly off-limits.
Section 2. Thinking tokens, cognitive allocation. Okay, so with our rigid boundaries firmly in place, the next vital step is managing the agent's cognitive effort and system resources. Context windows are finite, right? And deep reasoning takes time and compute. I want you to picture a physical throttle slider right there on your desk. You need to know exactly when to push it forward and when to pull it back. You're going to crank that throttle up to allocate high token budgets for the incredibly difficult tasks. We're talking designing complex distributed architectures, tracking down nasty race condition bugs, or executing massive multi-file refactors. But you pull that slider way down to minimal to save resources when the agent is just knocking out boilerplate scripts or standard unit tests. Mastering this token economics is absolutely essential so you don't exhaust your limits or create huge latency bottlenecks.
Section 3. Adversarial testing, pressure testing systems.
Now, before we ever let the agent push that throttle and actually write code, we enter a really critical deliberation phase to pressure test our system design. In advanced terminal agent harnesses, you have access to interactive routines built specifically for this. By invoking the /grillme command, you summon a specialized, friendly, analytical agent character. And this character's sole purpose isn't to write code, but to interrogate your logic. It reviews your implementation plans, your dependency manifests, your architectural goals, and it actively hunts for the holes you might have missed. Imagine this friendly, analytical character projecting thought bubble questions right into your workflow. It stops you in your tracks and asks something like, what happens to the authentication state if the database drops mid-transaction? It's actively looking for edge cases, missing security vectors, and architectural ambiguities. It forces this rigorous exploration and planning phase before any premature execution loops even kick off. And this is a game changer because it fundamentally prevents you from building on top of flawed assumptions. Section 4. Multi-agent systems, agent orchestration. So, once the plan is rock solid and our adversarial agent is satisfied, we move from deliberation into execution using advanced multi-agent topologies. When an autonomous agent executes a task, it doesn't just start blindly streaming unbounded terminal commands. Instead, it executes a highly structured deterministic loop. First, it observes. It gathers context from your files and those architectural invariants we talked about earlier. Second, it plans, churning out structured artifacts. Third, it acts, invoking tools deterministically, usually inside secure local sandboxes so it doesn't break anything. And finally, it verifies. It triggers automated self-correction loops by running your test suites. If a test fails, no big deal. The agent just reads the error, feeds it back into its context window, and iterates until those tests turn green.
You see, if you give one single agent the job of parsing, editing, testing, and documenting a massive codebase all by itself, its context window is going to pollute with noise and its performance will absolutely tank. So instead, we use a hierarchical orchestrator worker topology. Think of it like a team. A lead coordinator agent sits at the top. It maintains the primary context and breaks the big goal down into isolated subtasks. Then it dispatches worker agent A to, say, write unit tests in a temporary directory, while simultaneously sending worker agent B to refactor API endpoints in parallel. When they're done, they report back up to the coordinator. This completely isolates the work, prevents file write conflicts, and keeps that primary context window perfectly clean.
Section 5. Developer's new role, systems thinking.
All of these concepts point to a monumental shift in what it actually means to be a software engineer today. The modern developer's role has firmly migrated. You're no longer judged purely on your ability to memorize and spit out syntax. Your core competencies are now systems thinking skills. You have to master intent articulation, knowing exactly how to specify those constraints. You need context window management to prevent context decay and token bloat. You've got to know how to set iteration caps and circuit breakers so an agent doesn't just get stuck in an infinite loop, burning through all your API credits. And you have to be highly skilled at multi-agent supervisory control, orchestrating those hierarchical worker topologies. You are the architect, the supervisor, and the final safety gate.
As we wrap up this explainer, I really want you to step into this new world of autonomous execution with one thought firmly in your mind. The tools, the CLI harnesses, the multi-agent systems, they are incredibly powerful, yes, but they are entirely dependent on the boundaries and the logic that you provide. So ask yourself, when the AI writes the code, who architects the intent? Thank you for joining me, and I highly encourage you to completely rethink how you approach your next engineering project.